Alright, so here we are. We're going to do some integration using trigonometric substitutions, and this is where we usually change variables into trig functions. So we've taken expressions and replaced them with like a u, so gave them a new name, but usually something simple. But we're going to replace expressions or variables with actual trig functions like sine and cosine. So let's first see where this might come from. So let's start off here. I say consider basically a right triangle here. Maybe it's not marked as a right triangle, but you can deduce that from looking at it. And we put a angle theta in here. And we made some labels here. Across from the angle theta, we have an opposite side of length x, which is a variable. We have a hypotenuse of side length a, which is a constant number. So a would be a number, x would be a variable or an expression. And if we label those two things in that way, we can use Pythagorean theorem to solve for the base down here, which would be square root of a squared minus x squared. Okay? So these are just placeholders for whatever we would want to put here. So a could be 4, which means a squared would be 16. X could be 1/2 x, which means x squared would be 1/4 x squared. Okay? But if we set up this triangle, no calculus involved here yet, just set up this triangle, one thing we could say is the sine of the angle we're looking at, theta here, would be opposite over adjacent, so that would be x over a. Okay, sine theta is x over a. Now, if you wanted to try and reverse that and get theta by itself like we could later on, if we were solving for the angle, if we had both x and a, we could say that theta is the sine inverse or the arc sine of x over a. We could say many other things. I mean, we could use any trig function we want here, but the one that I have is the one that's going to be more useful than anything else. So if sine of theta is x over a, then we could also isolate the x here. If we got x by itself, then we'd just be multiplying by the a, so x is a times the sine of theta. Okay? So just going off this triangle, these are things that are easy to come up with. Now if we want to take the derivative of that, we could say the derivative of x, of course, is dx, and the derivative of a times sine of theta, a is a constant, sine of theta goes to cosine, and then we pick up a d theta. So you can kind of see where we're getting toward a possible substitution here. We were going to be able to replace x with some trig function, and then we're going to be able to replace dx with some trig function in terms of d theta. Now one more thing down here, I'll move me out of the way just so you can see. This cosine theta. Okay, if we want to take the cosine of this angle, it would be adjacent over hypotenuse. So that's square root of a squared minus x squared all over a. And what we're really going to be focusing on here in the long run is the square root part. Usually that's where we see the power in a trig substitution. We haven't seen a problem yet, but you'll see it in a moment. So if I wanted to get that by itself, I could multiply both sides by that a, and then my square root function here would be equal to a times cosine. So that's just a lot of generic information, but in this particular problem you'll see how it's going to be useful. So let's see the problem. We want to integrate the square root, what's a fraction, the square root on top of 9 minus w squared all over w squared in terms of dw. Okay? So when you look at this, you might consider a couple things. You're probably trying to rewrite the square root as something to the 1/2, and you might try a u substitution, but if your u is 9 minus w squared, your du does not have a square in it, so it doesn't really help. So a u substitution kind of falls flat here. You could try integration by parts, but then you have to kind of integrate something which you don't have the du on the outside of, so that kind of falls apart as well. So what we're going to do is we're going to take this idea of the trig triangle that we just saw. So relative to the triangle that we have, we can set this up because we see something that looks like the square root of a squared minus x squared. And in that case, it's the 9 minus w squared under that square root. So I can set up an angle in a right triangle. And if I let that be my leg down here, my base, Basically, that's 3 squared minus w squared for that base. So in that case, what we're saying is a is 3, and relative to what we've got, the x is w. So over here on the side, the opposite side is w, and the hypotenuse is 3. So if we took those 3 sides and put them in Pythagorean theorem, base squared, well, adjacent squared plus opposite squared equals hypotenuse squared, it would all balance out. But let's use what we've got here. Okay, so some things we can say here is that we can replace this numerator, the square root of 9 minus w squared, with something along this a cosine. So basically that means that my square root of 3 squared minus w squared, a little messy, let's clean it up. Would equal a, which is 3, times the cosine of theta. So I'm going to be able to replace that top part with 3 cosine theta. Okay, what else do I see in here? I see this w in the bottom, which from over here, x is w, so we'll be able to say w equals a sine, so that's 3 times sine of theta. Okay, and the last thing we have here is the dw, and with the dw, that's going to be relative to the dx. So dw, whether you want to take the derivative of the previous or use it from over here, will be 3 cosine of theta d theta. So we're going to replace those 3 things with what we have here. So what we have, we'll have the integration of 3 cosine on top over w squared, and w was 3 sine, so that'll be 9 sine squared, and dw is 3 cosine theta d theta. So let's go back to our color coding here and make sure you see where everything came from. Okay, so all these replacements. So if we clean that up, we have basically 9 cosine squared on top over 9, I don't know what happened there, over 9 sine squared d theta. Well, that's the same thing. The 9's would cancel out, so that's the same thing as saying we have cotangent squared of theta d theta, because cosine over sine, cosine over sine is cotangent. Here, hold on, let me pause for a second. Okay, sorry, I'm back now. So what we got here? We've got the integral of the cotangent squared. So this is kind of like a trig power rule we could do. We could replace the cotangent squared with basically cosecant squared minus 1. And that comes from a Pythagorean identity. It's, depending on how you want to look at it, you could say it's cotangent squared plus 1 equals cosecant squared, and just move the plus 1 over. But then you got 2 things you can integrate here, because you've got the integral of cosecant squared theta d theta. You don't have to separate them, but minus the integral of 1 d theta. So let's see what that gives you if you do that. And let's move me up here where I can be in the middle of your life. Let's see here. So if we do that, this is going to be, okay, I hit the button. Where'd my mouse go? The black. There we go. Okay, so the integral of cosecant squared is negative cotangent, and the integral of 1, that'll be minus theta, and there'll be a plus c out here. But take a look at what we've got here. We've got negative cotangent of theta minus theta plus c. I'll put a circle around that, but that's not where we can stop. The problem with this is we started with w, and now we're at theta. So we've got to get back to W. What's the relationship between theta and W? Well, we have some that we established here in the middle that we made the substitutions from, but really they came from this triangle up here. So we can go back to the triangle if we like. So if we want negative cotangent, we can come up here. Remember, cotangent is hypotenuse over, excuse me, not hypotenuse. Cotangent is adjacent over, no, opposite, yeah, adjacent over, cotangent is adjacent, which is cosine, over opposite, which is sine. Okay, so negative cotangent will be negative square root of 9 minus W squared, that's the adjacent side, over W squared. Okay, and then it'll be minus theta. Well, theta is going to have to come from something up here. So we could go back to where this thing was defined, and we could say, we could use the easiest definition we have here. We could use the opposite and adjacent. But to get back to theta, we'll need a inverse function. So the sine of theta is W over 3. So we'll say that theta is the inverse sine of W over 3, and then plus C. And a little note there, that inverse function, we could use pretty much any inverse function we wanted, as long as it's going to make sense. Okay, so just double checking here, cotangent is adjacent over opposite, so it looks a lot like the original problem in some way. Oh, why did I square that? No, that does not need to be W squared on the bottom, so let's fix that. I think I got struck by the original problem. There we go. Yeah, so negative square root of 9 minus W squared all over W, because that would be the adjacent over the opposite, minus the sine inverse of W over 3, because that would be the opposite over hypotenuse for the sine. Yeah, plus C. All right, we're going to use some of the other trig functions for substitutions, and we'll walk through that. Thank you.